For each of these, we're going to write the explicit formula, a sub n. We're going to call each of them a. And for them, we're also going to find the limit as n approaches infinity of the nth term, and the limit as n approaches infinity of the reciprocal of the nth term. What in the world am I talking about? Well, you'll see what I mean in a minute. So let's just kind of jump in first, and we're going to do some pattern sniffing. We're going to find out what the patterns are. So looking at this, from 2 to 7, I'd add 5 again, add 5 again. Okay, so just writing down a few basic thoughts. This one is arithmetic. Good to know. And because it's arithmetic, we can identify a few things. And what I want to identify, first of all, is that we're adding 5. So the common difference is 5. D is the variable we use for that quite frequently and most commonly because D stands for difference. And also, I want to identify that the first term is 2. And that's just good to know. So if I wanted the explicit formula, I could use the formula that was given to you in a previous video for an arithmetic sequence, series if we're adding. But basically what I'm going to do is kind of build it on my own again. So if I wanted to know any term, whatever the nth term was, I would definitely need to know where I start. And then I would need to add D a whole bunch of times. Well, how many times would I need to add it? Well, I would need to add it one less than the number of terms that I want. This thing is really out of focus. You better get in focus. There we go. That's better. So I'm going to multiply D times N. Well, this is incorrect. So here's the deal. If I wanted to go from 2 to 12, I would have to add 5 twice, but 12 is the third term. So I'm going to multiply by the, oops. Said 3 and wrote to 3. I really meant to write a 1. My whiteout's not behaving either. There we go, that's better. N minus 1. And I would multiply by 1 less than the number of terms that I have. So we have already come up with this. It was in a different video, but I just wanted to review it just so we can gain an understanding of the process that gets us there. So the nth term is 2 plus 5 n minus 1. This is totally acceptable. Let's go a little further. This is really 5n. That is 2 minus 5, so negative 3. This is also an expression for the nth term. So what I'm also going to do with a different color, let's use green, is find the limit as n approaches infinity of a sub n. What is a sub n? Well, a sub n is the expression, the explicit expression that would take us to whatever term we wanted, the nth term. So I want the limit as n approaches infinity of 5n minus 3. Okay, if you graphed this line, if you had the line 5x minus 3, it would go up forever. So this is infinity. That's it. So if we did the same thing, let's use red for the next one. If we did the same thing, only we did the reciprocal, n approaches infinity, of 1 over a sub n, so 1 over the explicit formula. Either one will do. This one's a little cleaner. So now if I were to find the limit as n approaches infinity, I would say, well, my denominator's getting really big. I have 1 over an enormous number. This is approaching 0. Interesting, huh? I think so. Here we go. Let's keep going. The next one is 2, negative 8, positive 32, negative 128. Well, first of all, we realize that the numbers are alternating. Second of all, assuming that well, if we just pretended like everything was positive, it'd be 2, 8, 32, 128. So we're multiplying by 4. We are multiplying, which makes this one geometric. There's a whole lesson devoted to this one, to geometric series. It's great. And our common ratio is the number we're multiplying by, which is 4. But I lied, it's actually negative 4. And it's good to know that our first term is 2. You don't have to write that, but there it is. So let's write the explicit form of a geometric sequence. Here it is. It would be my first term, and if I wanted to get to any other term, I would have to multiply by my common ratio. How many times would I multiply? Well, same as I did here, I would have to multiply by r repeatedly. So repeated multiplication is an exponent. So n minus 1, it would be 1 less than whatever term I'm wanting. So again, for example, if I wanted to get to like 128, negative 128, I would have to multiply by my common ratio 3 times. So to get to the fourth term, I would need to multiply by r 3 times. Okay, let's fill in some numbers. A sub n equals 2, negative 4 to the n minus 1. This is totally acceptable, but I think it's a really good opportunity for us to continue to work on this and just clean it up a little bit. So let's bring this over here. This is 2 times negative 4 to the n times negative 4 to the negative 1. Oops, negative 4 to the negative 1. There we go. That's better. Not much better, but it's better. Let's clean that up a little bit. It just looks sloppy. Negative 4 to the negative 1. And we'll take this negative 4 to the negative 1, we'll send it to the denominator, and we'll bring this work down here. So 2 divided by negative 4 times negative 4 to the n. So this became denominator, and that really gives me negative 1/2 negative 4 to the n. Okay, I have an explicit formula, and so what I want to do now is find the limit of each of these. So let's find the limit as n approaches infinity of the explicit formula, which we just found. That's a little nastier. This is a little bit cleaner, and it is negative 1/2, and then negative 4 to the n. And there is actually a little bit more cleaning we could potentially do on this. Yeah, I don't know how clean it would be, but we can talk about the fact that this is alternating. We're going to get to alternating series later. That's one of the reasons my mind went there. Anyway, let's move on. So the limit of this whole thing right here is, okay, let's just not even think too hard about the structure of this, although I think we could use that. Let's go here. Are these numbers getting closer to 0 or further away from 0? Well, they're getting further away from 0. So, well, are they approaching positive infinity or negative infinity? Well, both, because the signs are alternating. So I'm reluctant to even put an equal mark there. Let me take that off. I'm going to just say that this limit does not exist. It doesn't equal infinity. You could say this doesn't exist either, but it does approach infinity. This one does not approach infinity or negative infinity. Neither really. So again, if we approach this from a different perspective, if I said, oh, my infinity is an exponent, not really, but using it kind of theoretically, then I would have negative 4 to a huge power, and then I have an enormous number, and that enormous number is just going to make this thing blow up, which is why this does not exist. All right, let's switch colors and find the limit of the reciprocal. This is going to start going a little bit faster because you've seen this idea before. So 1 over negative 1/2 negative 4 to the n. Okay, so now the question is, if I divided each of these, if I said 1 over 2, 1 over negative 8, 1 over 32, 1 over negative 128, what's happening to my numbers? That's essentially what this is saying. So what's happening here? 1/2, okay? Then negative 1/8, then 1 over 32, then negative 1 over 128. As I do that, these numbers are getting closer and closer to 0. They are alternating, yes, but they're still approaching 0. They're approaching it kind of staggered, but they're approaching 0. Okay, there's 3 more on here, and I'm going to speed this up a little bit because the first one is arithmetic. Second one is geometric. These are neither of those. They're just kind of different, and we have to, well, pattern sniff. So let's find them. Sometimes you just have to look and see what you're dealing with and go from there. So in this case, we have 2, 5, 10, 17, and you might be like, wait, I don't recognize that pattern at all. Are we adding the same thing every time? Well, plus 3, plus 5, plus 7. Look, I hear you. There is a pattern to what you're adding. You're adding 2 more each time. Plus 7, the next one will be plus 9. But that's not just straight up arithmetic. Otherwise, you'd have a constant number you're adding every time, not a number you're adding every time and then a couple more, and then a couple more, and then a couple more. Actually, this one's going to be quadratic, and I want to make it fairly obvious. This is 1 plus 1, comma, 4 plus 1, comma, 9 plus 1, comma, 16 plus 1, comma. Okay, sometimes your mind just goes there. And so I'm hoping that in the process of doing this, you're beginning to realize that sometimes you look at that and you realize, oh, well, this is just one more than the perfect squares. So again, not arithmetic, not geometric. So you just kind of find the pattern. Here we go. The nth term does not have an explicit formula for it. But if I wanted any given term, I would take whatever term I'm on, first term, second term, third term, fourth term. I would take whatever term I'm on and I would square it. And then I would add 1. All right, the next part's going to go really fast because you've seen this before. The limit as n approaches infinity of this explicit equation. Notice how much shorter that work was there. Okay, what happens to this graph? If I'd graphed it like a parabola, x squared plus 1 just goes up, so infinity you could say doesn't exist, but it does tend toward infinity. All right, switching colors again. The limit, as in approaches infinity, of the reciprocal of that, that would be, well, 1 over enormous is 0. Okay, next one. Not obvious at all. Not obvious at all, but I'm going to try to make it obvious. I'm really going to try. So here we go. Sometimes you just get a sequence in your head that you notice, like 1, 4, 9, 16. In this case, it's 1, 2, 6, 24, 120, 720. Okay, I left some gaps in there. 0 is 1 minus 1. Then we have 2 minus 1, then we have 6 minus 1, then we have 24 minus 1, then 120 minus 1, then 720 minus 1, and it keeps going. Now, do you recognize that pattern? We just did it in the previous video. These are factorials. This is 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5, 6. So it helps if we notice and remember these basic sequences. The purpose of this lesson is so we can gain an understanding of some of the more basic aspects of it. So when we encounter it later, we'll know what to do. So a sub n equals whatever term I'm on, first, second, third, fourth, fifth, sixth. It would be that factorial, and then subtract 1. Okay, the limit, as n approaches infinity, of n factorial minus 1 is, well, this blows up, and it blows up fast. Factorials have an incredible magnitude. All right, well, if we have 1 over a factorial, minus 1, that minus 1 doesn't really impact where this approaches, but we'll put it anyway. 1 over n factorial minus 1. Well, n factorial is huge. We have 1 over huge gives us 0. We approach 0, I should say. Okay, last one is still not obvious, right? So I'm going to rewrite it because I know what I'm looking for. I know exactly where this is going. So we're going to do a little bit of a rewrite on this thing. So I see fractions, and I want to make everything a fraction. Why? Because it just helps me wrap my mind around it. So let's see. 1, 2, 3, 2, 5. Those are my numerators. Why don't we count instead? Why don't we count 1, 2, 3, 4, 5? Okay, well, you can't just change it. Yes, I can. Let's make this 5 over 24. Let's make this 2 into a 4 by doubling that, so we double that. Yes, we could reduce it to go backwards, but we're looking for a pattern. Okay, this one didn't change. This one didn't change. Put it over 1. This one didn't change. Put it over 1. Okay, so what are we dealing with now? All right, well, let's go for the obvious. The numerators are counting up. The denominators are looking a lot like 1, 2, 6, 24, but there's this extra guy right here. Okay, so let's just start with what we know. Here's what we know. We have a fraction, and the numerator is whatever term we're on, and the denominator is factorial, but it's not, because there's this guy. And so it's time that I taught you something that just used to confuse me to death, and then I watched a YouTube video on it, and it really helped me so much, but it's this. You'd think it's not, but it is. 0 factorial is 1. And previous explanation was, if I have 1 pet, I could take it in one way. If I have 0 pets, there's one way I could take this pet into the vet, and that's to not take it. Now, that's a really lame argument. There are much better mathematical explanations, but 0 factorial is 1. So 0 factorial is 1, 1 factorial is also 1, 2 factorial is 2, and then 3 factorial is 6. And you can see where this is going, and there's some more scrap work down here. But anyway, this is 0 factorial. So what I really have, and I'm just going to use different color. This is 0 factorial. This is 1 factorial. This is 2 factorial. This is 3 factorial. Now, if you're probably still reeling over the fact that 0 factorial is 1, Google it. Why is 0 factorial 1? It's great explanation that I did not do justice to. So if I'm on the first term, but I want a 0 in the denominator, now I don't want to divide by 0, let's be clear, but I do want a 0 to appear in my denominator. I'm on the first term, but I want there to be a 0, I'd subtract 1. If I'm in the second term, but I want there to be a 1, I'd subtract 1. I have a 3, but I want it to be a 2, I subtract 1. So whatever term I'm on, I would subtract 1, and I would do the factorial of that. Okay? Excuse me. Oh, yes. Bless me. The limit is n approaches. Whew, I feel better now. I keep teaching for days. Too bad we're on the last one. N over n minus 1 factorial. Okay, let's look at magnitudes here. The magnitude of this guy right here is going to be, sorry, I'm looking at something else. Sorry. I was looking at some previous work I had done on this, and I'm comparing. Like, did I explain it right? Yes, I did. Okay, good. Sorry. Moving on. The limit for this one, I have to compare magnitudes. I have linear divided by factorial. Even though I'm subtracting 1, factorial is just massive and blows up quickly. So denominator overpowers numerator. That's 0. In case you care what I was looking at, and you don't, but I'm going to tell you anyway. I was looking to see if I can simplify this in any way, and I really can't. It's not going to be simplifiable, because in a previous video we had reduced things like this, but considering that this starts at n minus 1 and goes n minus 2, n minus 3, n minus 4, nothing would cancel out. So that's what I'm thinking. All right, this one is the reciprocal of that, so instead of doing 1 over this, I'm just going to flip this thing over. Let's reciprocate. That's the better vocabulary. And who's more powerful, numerator or denominator? Well, definitely the numerator, so this is going to tend towards infinity.